Righto. Well, I hope everyone can hear me out there in webinar land. So welcome everyone to the webinar. This is the second of the series of a extension outreach project, which is funded by CRDC, CA and CSD as partners with the federal government of Ag. Look, this particular project's designed to raise awareness on greenhouse gases and encourage best practice. And I would like to introduce Chris Dowling, who's already run 21 workshops in cotton areas in the last 18 months. The material in the first two sessions will replicate those, so anyone who went on yesterday would know that. So Chris, for any of you that doesn't know, has over 20 years experience working for Incitec Pivot in a previous role, and now he's a consulting nutritionist for back paddock, specialising in broadacre nutrition. So if you've got a question, please write them on the dashboard and I'll go to them at the end. The webinar will be recorded and there'll be a link on the CottonInfo site. And look, when we're finished, we'll try and get as much discussion as we can and we'll see how we go. So Chris, over to you and we'll go from there.
Good, thanks Jeff, and welcome to session 2 if you were online with us yesterday, and also welcome to those people that have that started up today. So in following on from what we talked about yesterday,
the broadcast is now starting. All attendees are in listen-only mode.
Sorry about that.
Yeah, sorry, my my PowerPoint just decided to restart itself just as just as we get underway, which is okay. I'll just roll through to where we're supposed to be. Just hopefully this doesn't happen again. As I was saying yesterday, we talked about the large regional differences of drivers of what drives nutrient requirement from and makes different regions different in managing nutrients, and to a degree how seasons impact with management. Today we're going to sort of move on to looking in more detail at the individual paddock, or on a farm or a paddock, or even a sub-paddock level of things that affect nitrogen demand of the crop, the availability, and hence the use efficiency. Largely along the lines, you know, as this project is largely looking at nitrogen use efficiency, and in particular reducing the emissions loss through greenhouse gases, looking at the loss pathways, the size, importance, looking at measures of nitrogen use efficiency, and there are a couple that we can calculate fairly easily from a cotton crop, some not so easy, and just how we might interpret those. Because it is important, as I said, finished up saying yesterday, is we can't go forward until we know where we are now with nitrogen use efficiency. It's really about looking back at the records that we have of what we've done in the past that can tell us about whether how fast or how much opportunity there is for moving forward for the future. Looking at some of the tools for managing nitrogen use efficiency, in particular, you know, the role of soil and plant tissue testing, and just some of the best practices information that is available. So, you know, we are dealing with the nitrogen cycle. Largely the inputs we know about, and they consist of probably 3 main pools. As far as the crop is concerned, there's that's coming from the organic nitrogen or coming into the organic nitrogen pool or pre-exists there. So the humic fraction and residues from previous crops are part of the supply through to nitrate, which is predominantly where the plant takes it up. The other one, the other one is obviously the nitrogen that's resident in the soil at the time with soil sample or resident in the soil at the time we plant the crop. And if those two pools can't meet the plant's requirement, we then add fertiliser to top it up. Now, the issue we have, I suppose, is trying to be as efficient as possible, is making sure that those three pools, that being organic matter, soil resident nitrogen, the residual nitrogen from the previous crop and fallow, and the fertiliser we add, are done at high or are taken up at high efficiency and just meet the crop requirement for the yield. That's the ideal balance, but obviously things can go wrong, and in particular the large one that can go wrong are obviously the loss processes. And this one's coming in slowly, not because it's a slow process, it's to highlight that's the one that is potentially the biggest one or the biggest concern for irrigated cotton. That's the one that seems to be controlling the nitrogen use efficiency to a large degree, or the losses. So trying to if we identify that as being, if we've got runoff and erosion under control, leachings, we're usually doing a reasonable job with water because it's so valuable. Volatilisation losses are associated with particular application practices. Then our biggest risk in irrigated cotton is this denitrification component. So to increase efficiency, it's largely about trying to decrease that somehow. And that's what today's about, is trying to talk about how does that, how do we do that? So when we look at some of Rocky's data on the fate of nitrogen, there's a couple of things that emerge quite starkly. Is that when this green group here of bars is basically the end recovered by the cotton crop. You can see as the yield goes up, then as does the nitrogen fertiliser supplied, the nitrogen used goes up, and we come to a plateau where yield has plateaued out, and then we start to get an accumulation of nitrogen initially in the soil. So the plant's not 100% efficient at taking up water or nitrogen from the soil, so there's some resides in there initially. And if it's residing in the soil, that's not a problem, because it means we can recover it in the next crop, whatever that is, if we don't have any loss processes in the fallow process. The bigger concern is, we have losses that increasingly are end losses from the system that accumulate, particularly once we get to rates of nutrient that are in excess of what the crop is taking up or what it's using. So our loss from the system, mostly around denitrification and possibly some through water, tailwater movement, increase as we've got more nitrogen there that the crop hasn't used. And that really focuses on one of the very critical things about increasing nitrogen use efficiency is making sure that the actual rate that we put on matches the yield that we can achieve. So not oversupplying and trying to drive yield by putting more nitrogen on. The nitrogen that we apply should be to supply the yield potential, not to drive the yield potential. And there is a subtle difference there, but doing it the wrong way will only tend to cause low use efficiency and high emissions. So the question is, how good is current management? And I showed this diagram yesterday. It is not hard to get into a car these days and figure out what the fuel consumption efficiency is. And when you consider, the amount of money that we spend on fuel in a car on a farm versus the fertiliser bill, in those 20-odd workshops I've talked to farmers over the last 18 months, I always ask the question, what is your grain nitrogen efficiency, say for wheat, or what is your cotton nitrogen efficiency for cotton? And it is very rare that someone can tell me what that number might be for last year or any seasons in the past. That's going to be something that needs to be top of mind, probably as much as knowing the fuel consumption. I think it's partly because people haven't known how easy it is to calculate it and then how to interpret it. But in looking at where we want to go, we've got to know where we are and where we have been in the past, because obviously in any one season there are a lot of factors that can affect the efficiency. And knowing the variability that has happened in the past is important in knowing where to go for the future, and to help sort out some of the years and practices that may have been imposed on the crops that have produced high efficiency in the past. So when we're starting to look at how do we improve this, the easy thing to do is go and reduce the rate of fertiliser, or split apply it, or change the type of product, or put it deeper, or something like that. I call that a tactical approach. They're short-term activities around the application. But by and large, unless you understand what the cause of the low efficiency is, or the high emissions, then that may not be the right thing to do. And I think in assessing any soil fertility issue, there's two components we need to consider. One being the strategic level of assessing the longer term issues and trying to get on top of the cause of the problem rather than patching up the problem when it occurs. And in doing that, it means we've got to have a look at things like soil structure, irrigation layout, levels that are appropriate, rotations, to try and get around the conditions that underlie the causes of nitrogen emissions and low efficiency. Then apply the tactics that are most appropriate for that situation, or for that situation, until we can strategically change the soil or the irrigation. The use of fertiliser products and that is really only a set of tactics to bolster, in the short term, a problem that we've identified. As far as tactics, as I've said, the types of things we've got are changing the nutrient source, application rate, timing, methods of application. And as I said yesterday, as far as increasing efficiency, there's only two things that you can do. You can either increase the yield for the same rate that you might have applied, or you can decrease the rate for the same yield that you've achieved. That will give, both those approaches will give you increased efficiency, and depending on the situation, either or of those might be appropriate. In doing this, I've got that title there upside down because I believe that we've possibly looked at that nitrogen management section as being the way to go about improving nitrogen use efficiency and reducing losses. I turn it on its head and suggest probably the first place to look at is the soil and irrigation limitations. When we're talking about denitrification losses, we're talking about losses that are related to watering events that cause waterlogging and the nitrogen that's present. So if the underlying problem can be fixed by fixing up physical limitations such as compaction, soil density, then it makes sense that we go there first and then take the pressure off trying to do things with rates and timings and application methods. I suppose once we get a more complete view of or a survey view of where people have achieved high use efficiency and hence low emissions, it I wouldn't doubt that it'll come down to situations where people have low physical limitations on water infiltration through either cultural practices. They have soils with good chemistry around clay soils, their structural stability, and they probably are doing a very good job with irrigation to make sure that waterlogging is measured in across the season in hours, not in days, and that's the key to part of the key to this. The other parts to it involve obviously if the nitrogen, if it's not there, then it can't be lost, but the crop also requires it. So we've got to have some there for the crop, but it's minimising the amount we've got there for any one loss event. And the other one is keeping an eye on the weather and making sure we're aware of risk around how much nitrogen's there and the limitations of the soil and irrigation in being able to avoid a loss event. So yesterday I went through the 6 common causes of low nitrogen use efficiency. Number 1 being oversupply, having a wrap around the arm. And there's no doubt when you look at a nitrogen response curve, the loss, when you're around the critical value, the loss from undersupplying it is probably greater than the economic loss for oversupplying it in most seasons. But the opposite is the case for the environmental and the efficiency point of view, that that oversupply gives you low use efficiency, whereas undersupply gives you a higher efficiency. The thing is to try and balance the two off into an acceptable range. So, you know, the other ones are around the plant not being able to get hold of the nitrogen and then end up in the plant where it's going to be counted as far as contributing to yield as related to the nitrogen that is available across the season. As far as how do we know that the nitrogen's being used efficiently, again we go back to both Rocky's work and how that relates to possibly international standards that might be known for cotton, and we have this measure that this diagram actually represents, which is I suppose across the world and as a standard is called a partial factor productivity of nitrogen, which is basically, as the graph or the x-axis there says, it's the yield in lint divided by the N rate, something that everybody has in their records. And what this is suggesting is that somewhere between about 12 and 17 kilograms of lint per kilogram of N supplied, we've got it about right as far as the nitrogen's concerned. That's a number that comes up, that numbers in that range are quite commonly quoted international literature as where the economic optimum fertiliser has been applied across a range of environments and production practices. By and large, there is recognition that probably 2/3 of the Australian irrigated industry is not actually meeting that at this stage. And there may be a range of reasons why, some valid, some not so valid. But it certainly provides you with an idea of how close you might be getting to an economic optimum. And as I said, the lower number being about 12 kilograms of lint per kilogram of N supplied. That's something that people, I think, can do in their head. It's not a hard thing to understand. You might say from, you know, the yield is driven by more than just the nitrogen fertiliser, and that's a valid point. It does, any yield is obviously includes any mineralised nitrogen and pre-existing nitrogen. But by concentrating on the N applied, people that are achieving high nitrogen use efficiency are indicating that they are taking into account those other supplies and making a good decision around the amount that they're applying. So it's quite a valid tool to be used as a starting point. There are other things that contribute to that understanding, or other indices, but that's a good one to start with because it's easy to calculate. Some of the others, so I've talked about the partial factor for N, very simple, yield divided by the fertiliser N rate. It's used in grain, and 40 to 70 is a good number, kilograms of grain per kilogram of N, and for cotton it would seem 12 to 17 is probably the range we're targeting. Another index that it is possible to get seed nitrogen, and this is really about saying how much nitrogen has been removed compared to what fertiliser nitrogen was supplied. Now for grain, the international standard is somewhere between 0.7 and 1 kilograms of grain removed per kilogram of N applied. Below 0.5 is potentially over fertilised, and above 1 is potentially mining. I had a quick look at some numbers because Sal gave me some seeds and some gin turnouts and some lint yields this year from her project at Dirranbandi, and they came out, the sites that were approaching 12 for high efficiency in this index were up in the 0.7, 0.8 in this index. So what this takes into account that the yield, the previous index doesn't, is the loading of seed. So, it was taken up, but it was loaded into the seed, which from an environmental point of view is important. From an economic point of view, it's not a very good thing to have too much nitrogen in the seed that you're not being paid for. So, but it does give you a feeling for there is another index there that takes up into account the nitrogen that's actually going into the seed that's not accounted for just on a lint basis. Not a bad index to know at the same time, just for a measurement of the seed nitrogen content for a field. When we look at the agronomic of efficiency, this one's a little harder to get because very few people would want to put down a zero strip. And this efficiency is basically how much is the fertiliser increasing my yield, or how effectively is that increasing my yield. And for cotton, somewhere between 5 to 10 kilograms of lint per kilogram of N applied would appear to be somewhere we would like to be getting. So that's another index, a little bit harder to get because people are very hesitant at putting zero strips in. We could possibly do that on the basis of an incremental. So what's the difference between 100, 200, 300, and look at the efficiency of those increments as well as another way of doing that. The other reason why that's important is because we can turn that into dollars as well. If we know how many dollars we're getting from the lint and how many dollars it's costing for the nitrogen, we get an idea of the economic return from the nitrogen just based on the price of nitrogen, and to potentially any risks that we might be taking given the margin between the two. So turning that into dollars would be a useful thing. So there's some pretty easy indices, and there is no doubt that high nitrogen use efficiency, the research says that if we achieve the 12 to 18 kilograms, or 12 to 17 kilograms of partial factor productivity, and up around the 0.7 to 1 kilogram removed per kilogram of applied, our emissions are likely to be low. Just looking at the relationship between efficiency and dollars, and why people probably haven't focused too much on efficiency before. This is just an example from a strip from Nigel Corish at Yumbacully from last year, and it's probably pretty typical of what happens on a large-scale farm. Remembering that a lot of the efficiency information that we have has probably been done on research stations to set what the ultimate level that we can achieve. These numbers at the top here are the rates that were applied, and you can see as we go lower in the rates, the efficiencies become higher. At the most economic rate, this is the net fertiliser margin that was calculated. This wasn't meeting the efficiency guidelines. So that gap there suggests that there may be some limitations around, or some opportunity to improve the economics and the efficiency by understanding what's causing the gap between the economic optimum and the efficiency optimum that we're looking for. And those soils are not easy soils by any means, being sodic in the subsoil. So there's some challenges there in moving that up, but I think we understand what the cause of some of those challenges are, and they're soils based, and a process of strategic review of how to move that would help. So once we've identified the cause of it, yes, we go back to the 4 R's, rate, time, place, source of product, to improve the situation. And it'll be a mixture of those things. And it may be the fact that people decide on paddocks that have inherent soil structural faults through the chemistry, sodicity, magnesium, salinity, some of those sorts of things, that it is chosen to be high frequency rotations on those ones with cereal crops to help with the structural integrity of the soil, and those ones have a different irrigation regime and a nitrogen strategy that's based around that. Whereas other paddocks that on the same farm that may not have those inherent problems may be permanent back-to-back paddocks and with a different strategy. So they're the sorts of things I'm talking about, to start to segment paddocks on the basis of their nitrogen use efficiency and what might be driving those in particular situations, to come up with customised programs for fields with problems. The other, one of the other challenges that I suppose that we have with the efficiency is as we push yield upwards, and this is some of Rocky's data from a few years ago, inherently we use efficiency. So around the 4 to 6 bales per hectare, currently we require about 11 to 12 kilograms of N uptake to produce a bale. So 6 bales takes uptake of about 60 to 70 kilograms of uptake. And if you double that, that means about 140 N in the soil across the season to be able to supply a crop of that size. The challenge is the law of diminishing returns. The harder we push up against higher yields, our requirement goes up per bale, which means we've got to add more nitrogen to the soil and push against the inefficiency of uptake. The challenge for, as we push towards higher yields, is to make sure we're trying to keep the efficiency as high as possible and not letting it blow out past what we really require. So there is an inherent inefficiency in pushing for yields higher than they need to be, or in terms of over-fertilising, targeting yields and putting on rates of nitrogen that are not appropriate for the yield that's achieved. We get asked about new varieties of nitrogen removal. This is a representation of what has happened with the new smaller seeded varieties. With the old ones at 38% turnout and 3.5% nitrogen, having a removal around 13, and the new varieties at 4% nitrogen and 42. Probably not a lot that's really changed. So we can't. There's no justification of higher removal based on the new varieties because of that smaller seed. In fact, it is probably a slight improvement on the removal and hence efficiency of nitrogen use from those new smaller seeded varieties. So just exploring quickly the variables that affect N rate. I've taken these images from Nutrologic, which if people haven't had a look at it. Throws together some of the variables that affect nitrogen efficiency in any particular area. And as I described yesterday, one of the ones that drives the potential or the rate of development of the crop is obviously temperature. The faster the degrees accumulate for any particular yield, we tend to need a higher nitrogen rate to produce that, because we're trying to produce it quickly. Therefore, we need to have ready supply to drive the nitrogen into the crop. So when we're taking into account what nitrogen or how to come up with a nitrogen rate, it is important to recognise where you are, how hot it is, and that does affect the rate. Now, if you're in an area, obviously you're not going to change. If you're a grower in an area, your paddock doesn't change in area, but I can assure you seasons do change. And we get hotter seasons and we get cooler seasons. And I'll show you the difference between a hotter season and a colder season, in terms of what does it look like for the effect of heat on nitrogen requirement based on location. So with a lot of the cotton industry, the Guida and McIntyre valleys and that central growing area in New South Wales is a value of 1. Relatively the very hot areas, and the very hot areas being Burke, Emerald, St George, those areas require about 18% more nitrogen to grow the equivalent yield of somewhere around Moree, Narrabri. And the very cold areas, because they develop over a long period of time, have a lot of mineralisation potential across the season, a longer time to take it up, relatively only run about 70, have a requirement about 25 to 28% lower in those very cold areas. Now, very cold is basically the eastern parts, excuse me, the Liverpool Plains. That's not as you go south it gets colder. The coldest areas are the eastern and southerly areas, not the southwestern areas. And getting yield right is getting the nitrogen rate for the yield is very important. As described yesterday, the time to 60% open bowls on average since 1996 across the 1996 to 2012 when I did this graph, you can see in Emerald to grow a crop of 10 bales they need 145 days. If you grew the same yield at hay, it would take 203 days. A lot more time to accumulate nitrogen, therefore the intensity in Emerald is so much higher, we need a higher concentration. Another variable is the soil structure. So if you come in and use the decision support, you'll see that there's a factor of compaction in there. Obviously, the first thing you need to do if you do have compaction is adjust the yield to something that you can possibly grow with the compaction that's inherent. Trying to overcome compaction with nitrogen doesn't work. It just drives your efficiency down, your emissions up, and you achieve a lower yield anyway. So be realistic. If you do end up with a wet pick and a bad compaction year, adjust the yield realistically for the compaction, and then the software will adjust the rate of nitrogen required to achieve that yield with a lower efficiency. The types of adjustments that are made is basically with no compaction we get an index of 1. some compaction. You know, it's basically up to a 20% increase in the amount required for a high compaction situation compared to none for the same yield. Another variable is the soil type. Nitrogen's taken up through a process called mass flow, which is the water moving through the soil from a point of where the root is drying it out from a wetter part of soil, and the nitrogen flows with it. That flow is slowest in heavy clay soils and quickest in loamier soil. So there is an adjustment for soil type as well. It is quite well established that on farms, loamier patches tend to be more vigorous, you know, even if patches in paddocks where there are loamier patches, then the crop tends to get away with a lower rate of nitrogen, and that is an adjustment we need to recognise as far as the soil texture goes. So there's about a 15% adjustment around the median, which is a medium clay, which is most of the industry, but there's about a 10% adjustment either way for soil texture. Probably the largest effect in determining the efficiency of uptake and ultimately the rate, and all of these things I'm talking about go to actually manipulating the efficiency factor for which the nitrogen is taken up. So there's a cropping history, so it's the rotation as to what crops were grown previously that might affect either one, the structure of the soil, in other words, cereals versus legumes versus cotton, and the nitrogen contribution from the residues of those crops that were grown previously, either being cereals or legumes. So when you look at the relative value of various crops, you can see the base efficiency is set around cotton on cotton, and where there are large structural changes, likely such as where you've got cereal and fallow together, you can see the efficiency is bumped up quite dramatically by having a cereal and a fallow versus having cotton and a fallow, longer fallows and legume fallow. The thing that I suppose is this highlights is structure is very important, or the structural effect of a fallow is very important in getting higher efficiency. Less important is the contribution from legumes that may have been the last crop grown. So, you know, it takes into account the relativity between the structural effect given by cereals or fallows versus the slow release nitrogen effect that you might get from a legume. So, you know, what we're about in trying to get the nitrogen supply is trying to get a good balance between what the crop requires and what the soil can give up. You know, nitrogen soil testing is part of that, but it only gives us generally a view of the soil residual nitrogen and some feeling for the mineralization pool from the background organic matter. And one of the missing fractions, and I suppose the challenges to getting the nitrogen rate, is understanding what the previous crops are going to supply. But the things that affect these net efficiencies, because each of the pools that we get nitrogen from has a different efficiency factor. So the humic fraction, the things that release slowly in crop, like that humic fraction breakdown and residue breakdown, have a higher efficiency than the soil residual mineral nitrogen and the fertiliser nitrogen. And irrigation water has a different efficiency as well, where we're recycling nitrogen. It's the added effect of those that it becomes the added nitrogen supply, and therein lies the complexity of trying to estimate the nitrogen supply in any one season. That efficiency is made up of losses via these processes here. So, yes, it's not a simple equation, and it's not a simple fix, but a soil test is a starting point to understand, particularly if there's a large residual mineral pool, that really does need to be taken into account, not ignored. Mineralisation is important, and in doing some balance studies, it would appear that previous crops, even cotton on cotton, must be supplying somewhere between 80 and 100 kilograms of nitrogen per season. And it's something that, I suppose needs further study in the variability around that. But if you look at the mineralisation pattern of a cotton crop or cotton soil versus the uptake, that mineralisation can impact quite significantly a large part of the dry matter production or the nitrogen demand or the period of nitrogen demand in the crop right through to February. So it is important to take that into account, the potential for mineralisation to end up with a high nitrogen fertiliser use efficiency. As I said, the big question is around the denitrification process. This is probably the largest lost process, and it's something that takes place, irrigated cotton being on clay soils during summer. It is unavoidable. Every time people irrigate and there is nitrogen in the nitrate form in the soil, there are some losses. It's just a matter of how we control that and minimise the amount of loss each time we irrigate that is important in the long run. From an environmental point of view, Australia is judged on emission factors for industries, or the industries are accountable based on their emission factors. And you can see the recent research that's been done in cotton shows there are a range of emission factors for nitrous oxide from cotton production, and those ones that are the most concerning are where there is reasonable nitrogen in the soil at sowing or available for mineralisation, and the fertiliser rates are far in excess of what the actual crop can use, and we end up with emission factors 5 times what we would say is an acceptable amount, or the industry average. Where we under-fertilise, yes, we end up with low emission factors, but we also end up with low yield and poor profitability. So currently Australia, the cotton industry is judged at a 0.5, you can see, versus other industries, that have emissions, then cotton is probably in line with a lot of the other irrigated type production areas, whereas winter wheat and some of those other ones have lower emissions. So the big scale up is where we ignore the nitrogen that's totally available to the crop and apply a rate that's basically based on a formula irrespective of what's going to come out of the soil or pre-existed in the soil. So what we're talking about with denitrification is we've got nitrate in the soil, we've got oxygen decreasing because of either biological activity and or the exclusion of oxygen by water, in other words waterlogging. As the nitrate gets consumed by the bacteria in the soil, then nitrous oxides or nitrogen gases start to evolve, N2O, NO2, and then ultimately N2. These particular two gases are insoluble in water and are lighter than air, so they come out of the soil and are losses. N2O is particularly a problem, as is NO2, as they are greenhouse gases. N2 is not, but N2O, so small amounts of it are going to cause problems from a point of view. So what drives it? One is an oxygen deficit, which is usually coming from waterlogging. 2 is microorganisms present. We don't have many soils that are limited by microorganisms to drive this, so that's not likely. but the microorganisms need food, so if they don't have a food source, and they need nitrate to be present in the layer where the food source and the bacteria are. But when that happens, which is about 60% of water-filled porosity, that's when we're really getting things going. And that's not a soil that you'd say is necessarily waterlogged. There is still air there, but the bacteria are limited. So it's not that there's free water on the soil that denotes whether we're going to get losses or not. So in managing this process, there's a range of things. If this is a problem, then we've got to take into account things like the soil type. Is there something we can do with the soil to avoid waterlogging? Is there something we can do with irrigation that we can avoid waterlogging? So slope, angle and consistency, bed shape, application rate and method, tailwater removal speed, all of those things, what can we do there? And then once we recognise we're up to our limitations with what we can do there, then what can we do with products? So products that maintain in the ammonium form are not at risk of loss. So adding nitrification inhibitors comes into there of maintaining things in ammonium forms. The rate, we can avoid having large rates out there exposed for losses by split applying it or changing the application timing. So we're not risking having too much in the nitrate form in the soil at a time we have loss. The timing, it's really understanding the cumulative demand of the crop versus our application strategy and our irrigation cycles, and any limitations that are in there, and the methods of application. Are there differences between water running deep, shanking the stuff in, but there's also logistical issues around those. So there's a whole heap of things. We have some notion of how these contribute, and it's just a matter of going through in any situation where there is a low efficiency and a high emission potential to go through and work through in a logical manner of what's causing it and how do we either mitigate it by fixing the soil or the irrigation, or avoid it by changing our nitrogen supply tactics. So ammonium preferred to nitrate because we only lose from the nitrate form. There's little difference between unamended ammonium products, and there is some prospect of nitrification inhibitors or release modification products such as coatings to increase profit, but more particularly there's quite good information suggests they are very, very effective in reducing greenhouse gas emissions. So, based on the back of that, one of these would be DMPP and applied with anhydrous ammonia. The types of reductions in loss, that basically there was saving of 41% of the gas was being able to be avoided by the application of one of these nitrification inhibitors. So understanding when does the nitrogen require its peak amount. In the past, our application strategy has been around all pre-plant. That means everything east of this line or west of this line or above that curve is sitting down around there for denitrification events, potentially for loss events. So if we have 4 waterings before Christmas, then you're putting all of that amount of nitrogen subject to 4 denitrification events. The question is, if we have a pre-plant block and an in-plant crop block, then that there is potential saving because it wasn't actually subjected to those 4 irrigations before the crop actually required it. And that's the theory of side dressing. In soils where we have low potential for losses because they're well structured, irrigation strategies are very good, application strategies are very good in the placement of the nitrogen, then the potential savings are probably not a lot. But where we have situations with, and we can't avoid them with soils that are poorly structured, we've got problems with irrigation, that's probably where side dressing is going to have these types of savings. So it's not a one-shop fits all, but there are circumstances where it would make sense, and logic would suggest that split application is going to have more benefits than in others. And part of that is placement, getting nitrogen down to where it is below organic matter that's been incorporated, typically trying to get it deeper into the profile in bands, particularly for that pre-plant application, so we don't end up, as we understand it now from some of the work that's being done, is there is quite a significant denitrification loss from where we apply above the furrow. The nitrogen, the water wets up, brings it to the surface, and the irrigation water takes it away, and the product is denitrifying in the irrigation water, in the tailwater, rather than in the soil. Part of, I suppose, getting confidence with split application is maintaining control in season, and this is where leaf tissue and petiole analysis comes along, giving us some idea or some measure of what the crop is seeing across the season. There is an increasing trend to using this as another way of getting an objective measurement of what's happening with across the season, and understanding that leaf and petiole have different requirements is part of understanding how you might make this work. They have, to a large degree, somewhat of a bad reputation, and in my experience, a lot of that's on the basis of poor sampling strategies and poor understanding of just what's happening when we sample and what's appropriate, and the period where we should be making decisions and when we shouldn't. They work in small plots, they work in other places in the world. It's just about learning how to make it work for us as another index. And typically these are the types of decisions that we're making generally between the squaring and about 2 weeks after the start of bowl fill is the period where important decisions need to be made. And you know, the question is whether you add more, whether immediate reaction is required, do we delay it to the next test, or it's in excess and we've got to question what's going on around the strategy. So as experience moves along, we're getting more experience of how these work, and more confidence in making decisions based on that. Just a couple of examples of where things have gone, well, one where things have gone wrong. This is a site where the end of season rate was somewhere between 340, 360. The crop was struggling right through because this was 2010, a flood in November basically wiped out all the pre-plant nitrogen being applied, about 220 kilograms of pre-plant N, and then there was a lot of trouble trying to get nitrogen on because of the soil conditions, and never really got a rate on that was able to get the crop out of the problem it was in. It wavered around the cutout number, and it yielded about 9.5 bales. Another site, not the same site, but a similar sort of situation where the crop had the potential to be down here and continuing to go down. The grower had the foresight to recognise he'd had a large loss during that rainfall in that November, applied the nitrogen. 2 waterings later, we were back up to where it was a normal situation. Then a fairly orderly run through to the end of flowering, and a yield result that was probably a lot more acceptable, and it reflected in the way that the plant responded. So as far as where do I get more information on this, obviously there's quite a bit of information in the CottonInfo information, but also the fertiliser industry have recently produced Some best management practices are available from the website, including for nitrous oxide emissions from broadacre cropping, which includes cotton. So that's a simple sort of blow-by-blow description of the types of decisions around the 4 R's, the product, placement, timing, and method. And there's also a more detailed document looking at the process of loss and considering how that might happen in irrigation for people who want to read more deeply about the underlying loss processes. So, in this session, what we've tried to do is increase the, we're about trying to increase the profitability under higher NUE and decreasing emissions. It's a win-win if we can do it, and I think the technology's there. It's about knowing where to start and moving forward, and having the understanding that this is not a place that you get to. You don't get to higher nitrogen use efficiency. It's a journey. Each season will bring something different. Each season will bring a new challenge. But as long as in the long term we are heading in the right direction, despite the ups and downs of seasons, then we're going to be in a better place, both from a profitability point of view and an emissions and environmental point of view. So, if I was to summarise if someone asked me what should they go and do as a result of this, I would say first thing, go out and figure out where you are now. And the easiest way is to get your lint yield and divide by the nitrogen that was applied as fertiliser from all sources. That's starter, that's side dressing, that's all of the sources, and see where you sit relative to the magic number 12. The second part is to do, if you find your efficiencies are down in the 8.6s, 8s, and their consistency down there for a lot of seasons, and you need to look at a strategic review of the pathways of loss. Have a look at those 6 items I put up there as the pathways of inefficiency, and decide where that might be, and maybe seek some guidance as to further investigating and isolating the particular cause that might sit within that. Then there's a realignment of management strategies and tactics based on the inefficiencies, and then continue to monitor. So it's a process of continual improvement. But it is doable. There are people out there achieving it, and this season it would appear there was a marked improvement in efficiency this season based on just the fact that we didn't have any rainfall, and there were no irrigation or no losses based on irrigation that were compromised by rainfall events. So the efficiencies can be achieved in that range. It's not just research, but there's no doubt there are challenges for individuals with soils and climates that may and seasons that may not go with you. So look, I'll finish up there and pass it over to questions, and Jeff will probably moderate that the next few minutes for questions. Anyone there? Or
Oh, sorry, can you hear me now?
Yes, I can.
Sorry about that.
Yeah,
I did, unfortunately. So thanks for that, Chris, and I've got a few questions here, but type away, guys, and I'll get a few more to Chris while we've got him. We've got it's more a comment from Kieran down south with probably a question inside it, but he had a nil strip down there that went 13.2 bales to the hectare. But it was a bankless system, so I guess one of the queries I had was, does that make a difference being bankless? Is there a bit of movement of nitrogen across the field, or would it actually be a nil strip?
I suppose this. If you've got a nil strip that went 13 bales, it means that the nitrogen supply was quite good despite. So you'd question, where did that nitrogen come from? I'm not sure whether you could say that it was necessarily the bankless channels. As I said, it's got to come from three places. It's, maybe four if you count irrigation water or movement of nitrogen irrigation water, but it had to be in the soil at sowing, either from fertiliser or residual nitrogen or mineralisation. If it was a nil strip and it was at the bottom end of a field, then yes, I have seen situations where there's been up to 80 kilograms of nitrogen that has moved from head ditch to tail drain across a season.
Okay,
and
I guess with his, like, this is all the same bay with different rates across the bay, and I think he was wondering whether you can get movement across within a bay, a water.
Generally
bay.
not. Edge effects generally are, it depends on the size of the strip, but you wouldn't think you'd get an edge effect that was more than one row, particularly if you've got crop rows in between them. So, because, the one row will generally take up and show the effect of having had extra nitrogen supplied to it rather than the whole plot.
So it does start to beg the question, though, Chris, does it, that do we need to do nil strips to just see what our mineralisation levels are?
Oh, look, it would be fantastic if everybody could find it in their hearts to do one, because it would answer a lot of questions.
Yeah.
One, it helps us get a benchmark for the agronomic efficiency of nitrogen.
Yeah.
So what difference is the fertiliser making? And secondly, we really don't, other than in research plots, in field scale, do not have a good understanding of net mineralisation of either the humic fraction from our base organic carbon or the residues of the previous 2 or 3 crops prior to the one we're growing.
And potentially, could the mineralisation be less if more nitrogen's applied? Like, could it have an effect on mineralisation, the amount you put on?
No, it generally goes the other way. Nitrogen, particularly where it's cereal crops, added nitrogen usually has what's called a priming effect. So it provides enough protein for the bacteria to allow them to break the stubble down faster.
Yeah, right. Okay. Now I've got one from Johnny Welsh. NUE calculations need to include nitrate levels. What's your views on this?
Look, you could start to include as other indices other pools of nitrogen, but one that, I suppose the reason why we use the fertiliser rate and the yield is they are two quite closely defined numbers. Where we start adding in other things, other pools of nitrogen that might be available, then our confidence tends to, in what that number is on a paddock basis, because of variability and a range of other things, starts to waver. But yeah, yes, as long as we did, sampling, if we talked about soil nitrate, we'd have to be very careful about when we took it year to year to be able to compare between years. So if you took it in June, you might get a different number to September because of different mineralisation amounts.
Yeah, right.
And that's the challenge, is knowing that the cycle has reached the same point each year.
Yep, okay.
The only other way of doing it is doing it immediately post-harvest.
Yeah, right.
And we're using the residual nitrogen as a factor as well.
Okay. Now we've got Andrew Bullard. Have you been unmuted, Andrew? Can you speak and see if we can hear you? Oh, Andrew, you might have muted yourself. Can you unmute yourself? Are you there? We might just try. So Andrew, if you could just unmute yourself and we'll come back to you. We did have a second question there from Welshy. Do we know the losses at variable depths of a pre-plant N? Rocky is now recommending 400 mils depth for a pre-plant.
Well, the deeper the better, I would say. It just comes down to what's practical. Yeah, even down there, it's not necessarily safe. And I make that comment on the basis of a study that was done at not a cotton site, but the Colonsay long-term trial site, Insidex site on the Darling Downs, where excess nitrogen to crop demand has been applied in that site over a number of years, and it had built up a large body of nitrogen in the profile of the 120 kilogram plot. After the flood in, I think it was 2011, they had soil sampled it just prior to the flood, and they went out and sampled it again when they could get back on the ground, and 80 kilograms of nitrogen had been removed from as deep as 60 centimetres. 60 to 80 centimetres. So, you know, while ever you've got anaerobic conditions, nitrate, and some organic matter to be able to drive denitrification, then it will occur. Now, the thing that I suppose is in favour of going deeper is that soil temperatures are cooler, that the organic matter is lower. Therefore, if a waterlogging event was to come along, then relatively the losses will be slower and will peter out because of lack of energy for the bugs. So I would agree with that, and that's probably a good compromise between the logistics of pulling a tine through the soil and you know the amount of loss that the benefits from you get from going deeper.
Okay. Righto, Andrew. I think we're unmuted. Fire away.
Yes, thanks for that. I've over about a 15-year period used quite high levels of foliar fertilisers, which have reduced the need for putting in under the soil. I'm just wondering whether there's any factors involved in any of these surveys that you've presented.
Foliars, I suppose the question that would be posed about foliars is how much of it's actually going through the leaf and how much is actually ending up on the soil surface and then being taken up by root uptake. And it's the relativity of those. Obviously, as soon as it's on the soil surface, it's at risk of denitrification. On the plant surface, you've got some volatilization risk, yeah, you'd have to look at a particular circumstance to try and figure out where the nitrogen was actually getting into the crop.
Yeah, well, bearing in mind the research that we've done indicates that foliar unlocks the nutrient cycle quite quickly because it has an immediate effect, and the soil of putting a typical NPK application gives you what is posed to me as an 11,000 times more effective way of applying a remedy quite quickly. So it's quite interesting, but the foliar that we particularly used, as Stuart McFadden may remember, is is a formulation that's chelated, so it is available to the soil, and it doesn't tend to volatilize that quickly or get neutralized by contact with the soil. So it does have a beneficial effect in that area as well.
So we're talking about a nitrogen product here?
Yeah, an NPK typically.
So the nitrogen's chelated?
Yes, it is.
How can you chelate a negative ion?
That's done in the process of manufacture. It's a negative ion which is attractive to the plant because the plant tends to be positive. But I just know the product.
Chelates need a positive ion to chelate.
Yeah, look, this is getting a bit technical. I'd have to refer to some printed matter on that. But the chelated product.
Yeah, righto.
Yeah. Okay. Righto, well, moving on. We've got another question from Amanda down there saying, what is the formula to get seed end percentage to kilos of N per hectare?
So yes, you'll get if you send the seed away to a laboratory, they will do and send it back to you as generally as percent N,
Yeah.
and you want it as kilograms per hectare. Then you know it's given. Obviously, what you need to do is to take you've got to actually calculate what your seed yield is per hectare. So basically you've got your gin, which means you need your gin turnout, and you've got your yield, or if you're lucky enough to get your actual seed quantity from the field, then if you've got the seed in tonnes divided by the number of hectares, and then multiply it by you know 4 over 100. If the seed percent was 4%, then it's basically 4 on 100 times the seed amount per hectare. If you don't have the actual seed quantity or the amount of seed per hectare, then you've got to go through the process of reverse engineering from your yield and your gin turnout, the seed amount per hectare, which is basically your gin turnout taken away from 1. So if your gin turnout is 40% or 0.4, then the remainder it must be seed, and it could possibly be some gin trash, but let's just say it's seed. Then 60% of the weight of it is seed, and divide that into your yield to get an amount of seed, and then multiply that by the seed percentage. I probably should have put the formula up there, but you can get at it from either the yield and the lint yield and the gin turnout, or having the seed quantity per hectare produced, and then just multiplying that by the percentage of nitrogen in the seed.
Okay, righto, thanks for that. We've got a question from Alice Melland. Fire away, Alice.
Can you hear me now? Great. Sorry, I couldn't seem to type in the questions today. Hi, Chris. Thanks very much. I was just wondering regarding nitrogen surplus as opposed to use efficiency, so input minus removal. Have you got a sense of how they are relating to the nitrogen use efficiencies that you've been measuring across different properties, and how that is likely to change over time with some of the improvements in nitrogen use efficiency that people might be able to make with the various strategies that you're talking about and tactics? Because it seems to me that they're not mutually, like with nitrogen use efficiency going up, you can tend to also be increasing your surplus as well, if that's the tactic you use to increase. If you reduce the amount of input you need to increase yield, then you're going to chase more yield, you'll increase the inputs at the same time, and surplus can increase, and that can be available for loss.
Yeah, that was the point I was trying to make with that the efficiency or uptake, or the uptake of nitrogen as you push yield up increases. And there is obviously a natural and inherent inefficiency as we push into higher yields. Plants at that low yield appear to use and low nitrogen tend to use it very, very efficiently. But in sort of, I haven't really got the quantification, but just observation over probably over 10 or 15 years, that one of the measurements that I've seen that appears to occur is where a crop has used nitrogen efficiently and not suffered a yield problem. There is a range of nitrogen residual in the top 60 centimetres of soil that is quite acceptable. And that range is about between about 40 and 80 kilograms of nitrogen in the top 60 centimetres. It would seem that we can't extract everything. And then if we go much below 20 kilograms, if we end up with much below 20, there's a possibility the plant was having to forage too hard for it, and we may have actually been able to produce a little bit more yield by having some nitrogen there. So, and certainly in situations where there's been more than 100 kilograms left straight after harvest, the crops have generally been very vigorous and either have had poor yields with large bushes, they've had some sort of an event where they've lost the yield potential and that sink for nitrogen in the seed, or it's just been grossly over-fertilised. So to a degree I use the seed nitrogen, the soil residual nitrogen after harvest. This is immediately after harvest, not prior to the next crop, and a range of factors to assess just as well as efficiency as to how well the thing has gone.
Sure, okay.
Okay,
Thank
does that
you.
answer your question, Alice?
Yeah, no, I'm just wondering, if that surplus factor can be looked at or should be looked at the same time as chasing, improved efficiencies, just to look at the two in balance, because you can have, if you have 60% of a very big number is still going to have more surplus available than 40% of a small number. So if you've got a 60% efficient system but in a more intensive and higher input system, you're still going to have a larger potential for loss. So I'm just wondering whether, as an industry, both those figures can be looked at in tandem, as well as the detail that you're talking about when those surpluses are and where they are in the system.
Yeah, and I think that's what John was getting at about trying to, get a feel for the nitrate pool. But ultimately, being able to measure the total available and then what ended up actually being used, that net balances to what was likely lost, is a very difficult thing to actually get hold of in a field situation. So by using a multiple of, I suppose, factors, knowing what the starting soil then was, what was applied, having a reasonable estimation of mineralisation, and knowing what was left at the end by I suppose by inference, what is not in and what was taken up and removed by the crop, by inference what was not in those pools was lost.
Yeah.
Okay. Sorry, Alice. Thank you for that. So Andrew's got another question here. Are there any changes to NUE under drip irrigation versus, flood being bankless, I'm assuming, and furrow irrigation?
I would expect there possibly are. There are variations. You can have badly run drip irrigation because causing low efficiency. So it really just comes down to the amount of waterlogging you create relative to where the nitrogen is applied and where the organic matter is. So with any system, it is possible to produce waterlogging events in the zone where the nitrogen and the organic matter exist. The whole question around the denitrification and loss process is about in which soil and which system can we minimise the denitrification minutes, hours, days, weeks. And that it's really making sure that the irrigation method is optimised for the soil and the logistics of nitrogen use on the farm. One of the ways that you can avoid it, or that you get high use efficiency, is by using or changing the availability from pools, or the size of the pools that the crop gets it from, to those that provide nitrogen with the highest efficiency, which tend to be those that release nitrogen during each irrigation cycle based on wetting and drying cycles, which are the mineralisation processes.
Okay.
So having more fertile soils with higher residual nitrogen in the organic matter and lower fertiliser nitrogen is a path to higher efficiency, but it's not always possible economically.
Yep. Look, that's fantastic, Chris. I'm just cognizant of the time that we might cut out a little bit before 1:30. So thanks very much. It's always great to hear you speak, and we learn something every time we do it. So thanks again for these two webinars. And for anyone else, thanks for your input. Thanks for turning up, and it'll be on again tomorrow, but without Chris, I think. So thanks again, Chris.
I'll be listening in, John.
Righto. Thanks, everyone. We'll see you maybe tomorrow.
Thanks, everyone. Bye.